everyone, welcome to the lecture number 27 of this NPTEL lecture series on charging infrastructure, and we have discussed some part related to closed loop control, and let us continue our discussion in this lecture as well. So, our control objectives were to regulate the output voltage to a desired value, and at the same time we would like the current which is drawn from the source to be having a unity power factor operation. So, that means we do not want any phase angle between the current drawn and the voltage of the AC voltage source. So, this is the requirement. Now, in this we have seen that since to have the balanced 3 phase operation, this ISA plus ISB plus ISC equal to 0, that for balanced 3 phase operation. Not in order to, if you would like to, if you want to have that, then we could not able to control them independently. That means if we are changing the ISB value, automatically ISA and ISC value will change, and if we are trying to change the C value, ISA and ISB will change, and whenever you are changing the ISA value, ISB and ISC will be changing. So, that is why we need mechanism by which we can make the independent control of those currents in the 3 phases, and for that we have defined, we have defined the space vector, which is nothing but a vector which is rotating in a space with the same frequency as that of the frequency of variation of voltage, with respect to time. So, this space vector is the vector in the spatial domain, that means in the space it is rotating, and that speed with which it is rotating is same as that of the speed with which voltage is changing over the time t. And there we have seen that since the space vector is rotating in a 2-dimensional space, we need to provide the representative vector, and those representative vectors should be such that they are 90° apart from each other, and if they are 90° apart from each other, then we can ensure that the component of the space vector on those representative axes are independent of each other, and then we can control them, or we can change those values, those representative axis component, and that is when the change in one of the component will not have any impact on the other axis component. So, to do that we have defined 2 reference frames, and in that reference frame, first one is the alpha beta reference frame, which is nothing but the stationary reference frame, and the name itself says that alpha and beta are stationary, and so this space vector is rotating. However, the alpha and beta components are stationary with respect to this space vector, and that is when the component of space vector on the alpha axis and on the beta axis are actually independent of each other. That means when you are changing anything on the alpha component, there is no impact on the beta component, and whenever you are changing the beta component, there is no impact on the alpha component, primarily because when you take the beta axis component onto the alpha axis component, you will do V beta or Vs beta times cos 90, because they are 90° apart and cos 90 is 0. Similarly, we have defined another reference frame which is rotating reference frame, and why the name rotating reference frame? Because we have assumed that rotating reference frame are aligned along the space vector which itself is rotating with the speed omega. So, that is when the name comes. dq, d means direct axis, q means quadrature axis, they are 90° apart from each other, and d axis is aligned along one of the space vector, and they will be aligned during the entire operation of the converter, or you can say that during the entire line cycle of the voltage variation, or you can say the current variation. So, now we have also taken at any given instance of time, if ABC are sampled quantities, and sample quantity could be your Vs quantity or the supply voltage, 3 phase supply voltages. Your sample quantity could be Is quantity, which is the current drawn from the supply, and your component could be V converter, which is nothing but the voltage which is be applied at the output of the half bridges. And let us see one more example where, let us say this is your A axis, this is your B axis, and this is your C axis, and if we define the alpha beta axis, so alpha is aligned along the place where you will have the A axis peak, and then you have the beta component which is 90° from it, and let us say the Vs vector is somewhere your Vs vector is somewhere, let us define this as Vs vector. Let us take your Vs vector is somewhere here, you know, and that this is at, let's say, at given, you know, let's say this is theta 2, which is at given instance time t2, and this rotation is, you know, the angle at any given instant time t2. This is omega. Omega is nothing but 2 pi by t, 2 pi fs. So now at this is, let's say this is your Vs vector. So now let us define our dq component. If we try to define the dq component, now we know that our d axis component is always aligned across the along the Vs vector. So our d axis component, d axis is here, and the quadrature axis is 90 degree. Let us draw the 90 degree. So this is q component, and this angle is nothing but 90 degree. So this is how in the entire line cycle this dq axis, which are 90 degree separated from each other, will be rotating in the space going from 0 degree to coming back to the 360 degree. And this is why it is called as the rotating reference frame, sometimes also called as a synchronous rotating frame, because they are also rotating with the same speed as that of the speed with which the voltages are varying over the line cycle. And that is when we can define that this quantity. So similarly, following these formulas, we can also define Vs alpha, I mean the component of Vs space vector along the alpha axis. Vs alpha is nothing but 3 by 2 Vsa, which is the sampled A phase voltage value. Vs beta is nothing but you know, root 3 by 2 Vsb minus root 3 by 2 Vsc, where you can say Vsa, Vsb, Vsc are the sampled Vn of t, Vbn of t, and Vcn of t, one of the time instance. Similarly, we can define Vsd to be Vs alpha cos theta plus Vs beta sin theta, and we can define Vsq minus Vs alpha sin theta plus Vs beta cos theta. So we can also sample our ISA, ISB, ISC current. We can and then define Is alpha to be 3 by 2 ISA, Is beta to be root 3 by 2 ISB, and then minus root 3 by 2 ISC, where ISA, ISB, ISC are the sampled ISA, ISB, ISC currents. And similarly, you can also define ISD to be Is alpha cos theta and Is beta sin theta, and Isq to be minus Is alpha sin theta plus Is beta cos theta. And then similarly on the same line, if we assume we are applying the V converter voltage from the converter side, on the same line we can also write down our V converter alpha, V converter beta, V converter D, and V converter Q component. Here theta is equals to omega t, where t is the time instant when the samples are taken. Now let us try to model this converter in the dq axis or in the alpha beta axis frame, or synchronous rotating reference frame, or stationary reference frame. Now before that, let us try to also define one more thing. In this particular converter, we have assumed there is also a small resistance which is introduced because of this winding of this inductor, and this is nothing but the series resistance of inductance caused due to, we can say that caused due to winding resistance, you can say winding resistance. Generally the inductors are wounded over the core so that it has the winding resistance. These values are very small in milliohms. So now let us draw single phase equivalent of this one. So if we draw the single phase equivalence of this, so what we have is, again in fundamental frequency terms, fundamental frequency. So, what we have is we have Vs of t, we have Ls or we have L, and we have Rs, and then on the other side we have applying V converter of t, and there will be the current Is of t, current which is been drawn from the source, I mean obviously for the fundamental frequency component. So, now using this, let us try to draw, in the vector terms, let us try to draw this one. So, in the vector terms we can say this is nothing but the Vs space vector, we have L, this is Rs, and then this is another thing which is V converter space vector, and then you have Is space vector. Now, this space vector, this Vs, Is, V converter is actually the combined effect of all the three phases which we are talking about. So, now what we have is, let us try to draw using this thing. So, what we have is we have alpha axis, we have beta axis which is 90 degree from each other. So, we have alpha beta component, and then we will define our space vector Vs, let us say at some angle which is angle, let us say this is a theta angle, it is been drawn, and we know that we have V converter space vector, Vs space vector, and we have Is space vector. We have these three quantities which we have to draw. So, let me define, this is d axis is placed over here, and we have our q axis which is placed over there, and these two are 90 degree from each other. So, we have aligned our d axis along this Vs space vector, because we know that the supplies, I mean ABC phase voltages which we are applying are the one which is constant in a system. However, this ISA, I mean the current which has been drawn from the source depends upon the operation of this converter, and the V converter which is been applied is again dependent on the operation of the converter. It is only the Vs space vector which remains mostly constant and mostly fixed over the operation of the converter, since they are the supply voltages, and we assume the supply voltages will be having the balanced operation as well as the RMS values and peak values will be constant over the line cycle. So, it is one of the things which we can take the reference. It has minimal deviations. So, that is why we have aligned our d axis along the Vs space vector, and that is when we defined our q axis perpendicular to that. So, that means what? That means if we make this d component align along these Vs space vector, then we can ensure that the component of Vs space vector along the d axis, it is non-zero. However, the component of Vs space vector along the q axis is 0, and that is when, if we can ensure that this Vsq is 0, that is when we are ensuring that our d axis is aligning along the space vector Vs. Now, and this space vector is at theta, and which is defined as omega t, and let us define our V converter space vector. Let us define that V converter space vector at some angle. Let us define this as V converter space vector, and that is, let us say, is at angle delta. I mean this could be this side, this could be another side, I mean any side it could be. In general, let us define this at an angle delta. Similarly, we can also define space vector Is, or the current which is drawn from the source. So, this Is space vector will be, let us say, define it as at, let us say, here. However, we would like to ensure that Is vector to be aligned along the Vs space vector, but for a general case, let us say this one is at phi angle at some point of time. Let us take this has some phase angle. However, this is not we want to do in our operation, but for general case, let us define one quantity phi, which is a phase angle between Is space vector and the Vs space vector. Now, if you look very carefully in this particular space vector diagram, let us try to find out the alpha beta components and the dq components, and that is when we can define our models in the dq axis frame and alpha beta axis frames. So, let us try to write down the Vs space vector in dq axis terms. So, we can define, I mean, for dq plane or dq axis plane, we can define my Vs phasor is nothing but component of along the d axis, the component of Vs along the d axis, plus since these two d and q are 90 degree apart from each other. So, we will write j 0, j corresponds to the 90 degree. So, there is no Vsq component because our Vsq component is equals to 0. Why I can say q component is 0? As the Vs space vector is aligned along d axis. During operation, we will ensure that this d axis is aligned along the space vector Vs. Now, let us try to write the Vs space vector in terms of polar formation. So, it is magnitude of Vs space vector e raised to power 0. So, modulus is nothing but, you can say modulus Vs space vector is nothing but Vsd square plus Vsq square, which is 0 under root, and there is, since there is no Vsd vector, so we can say it is angle 0 with respect to d axis. Similarly, we can write alpha beta frame, we can write this is also, we can write, I mean, plane, or we can say dq frame to be more precise. So, for alpha beta frame, we can write Vs space vector to be equal to modulus Vs. So, the magnitude will remain be the same of this vector, because we have seen in the 360 period the magnitude of this Vs space vector will remain be the same. So, the amplitude will remain be the same. However, the angle to which this alpha and beta axis away from this dq is there. So, we will represent, since we are representing with respect to alpha beta plane, it will be e raised to power j theta, and that theta comes from the angle between dq and this thing. So, whatever my Vsd component is there, I will just take Vsd component cos theta to get the Vs alpha component, and Vsd component sin theta I will get the Vs beta component. However, there is no Vsq component, so that is 0. Now, we can also define for another quantities in the same line. We can define our Is space vector to be modulus Is e raised to power, you know, the angle with which it is with respect to dq is j phi, and similarly we can write V converter space vector is nothing but modulus of V converter, magnitude of V converter vector, and e raised to power j delta. Similarly, for alpha beta plane, we can write Is space vector to be modulus Is e raised to power, it is from alpha beta, it is theta plus phi. So, e raised to power theta plus phi, and we can say V converter space vector to be modulus of V converter. You can say angle wise, if we see, it is delta plus theta. So, it is theta plus delta, and this is the way by which we can move from one frame to another frame and another frame to that frame. And if you look very carefully, the magnitude of space vector is not changing, the amplitude will remain be the same. However, the angle with which for that frames will be different. So, here if we take alpha beta plane, so we can say, for example, if we write Is alpha, it will be nothing but modulus of Is cos theta plus phi, and I can write beta component Is beta to be, you know, magnitude of Is sin theta plus phi. So, that sine and cosine term will actually will give you the different values. And now, using this representation, let us try to obtain the single phase equivalent circuit model in alpha beta and dq frame, because if we model that circuit in alpha beta frame and dq frame, we can obtain the alpha beta dq components of currents, and then we can control those components independently. So, let us try to write down our equation first in the stationary frame, and then from the stationary frame we will move it to the rotating reference frame. So let us try to write down the circuit model in alpha beta stationary frame. So if we apply KVL, it is nothing but, we can write Vs space vector is nothing but L di by dt Is space vector plus R Is space vector plus my V converter, which is coming over there, V converter space vector. Now since I am writing it in the stationary frame, so I will write Vs space vector in alpha beta frame is nothing but Vs e raised to power j theta L d by dt is modulus I mean amplitude of Is time e raised to power j, Is is theta plus phi plus R plus V converter magnitude times e raised to power j theta plus delta. So this we got our alpha and beta stationary frame. Now let us move this term to the dq rotating frame. So let us write dq rotating frame or synchronous rotating frame. Let us write now this we will get, let us say this is the equation number 1, this we will get by multiplying equation number 1 by, because what we are doing, we are just shifting that alpha beta frame equation to the dq frame equation, and that we will get by subtracting the angle theta in all the vectors. So all the angles corresponds to the vectors are subtracted by angle theta. So we will get it by multiplying equation 1 by e raised to power j minus theta. Now that we will get by Vs e raised to power 0, because if we multiply this with, let us say, minus j theta L d by dt Is and this is again minus e power j theta plus R magnitude of Is space vector theta plus phi e raised to power minus j theta plus e raised to power j theta plus delta e raised to power minus j theta. Now this we can ensure, this is what we have is E j theta minus theta, so that is nothing but 0. This is L d by dt minus Is E j theta plus phi e raised to power minus j theta plus, again this e power minus j theta is outside the bracket, it is not inside the bracket, so that is there, and this one, this can be easily come inside the bracket, so that will become modulus Is e raised to power j theta plus phi minus theta, so that will be j phi plus V converter e power, see these are the exponential, this angle term, so they will be just multiplication will be added, so theta plus delta minus theta, so that will be just delta. And now if you look very carefully in equation number 2, okay, this is the term which has to be further segregated, because see this is not inside the d by dt term, this is the term which is actually varying with time, it has the magnitude Is, along with this it has the angle term, and we know that this angle term, this theta, is changes with time. because we know that our d theta by dt is nothing but omega. So that term will come into picture. So that is why we just cannot take directly this e power minus j theta inside. So let us represent this term in some other way. So let us try to write down these terms in this way, this particular term, simplifying this term. So we, for that, let us take one term L d by dt magnitude of space phasor is to e power minus j theta. Directly this we are taking. Now this term, now we can define this term to be u and this term to be v. So now there are two terms and both the terms are dependent on time. So we will use the differentiation of product of the terms. So what we will get is, we will get L coming out. First we will write d by dt e power theta plus phi, and this is e power minus j theta plus is e power j theta plus phi to d by dt of e power minus j theta. Now this term, if we see here, we can write this one as let us take the next side, which is L d by dt theta plus phi minus j theta is to be equal to, we can take L we take this one out, L di by is e power j theta plus phi e power minus j theta plus phi is e power j theta plus phi. Now we can write d by dt e minus j theta to be nothing but e power minus j theta times minus of d theta by dt, which is equal to e power minus theta minus omega. Now this, when we put this one here, we will get L d by dt minus modulus es e power j theta plus phi to e power minus j theta omega, and here again one L is come inside, will come inside, so this will be there. Now this we can rearrange this term and this term. So what we will get, L d by dt power j theta plus phi to e power minus j theta, this will go that side, is nothing but L modulus of I is space vector e power j. Now this we can take it inside, j theta phi minus theta plus, because it is inside the bracket we can take. Before that we have just represented in this manner, and this goes there, so that will be L is e power j theta plus phi minus theta, because this will go inside the this one into omega, and that we can say L is e power j theta plus phi minus theta is nothing but L so phi is e power j phi plus L omega, this theta theta will get cancelled, modulus I is e power j phi. And if we look very carefully, this is nothing but equation 3. So put equation 3 in 2. So whatever we have in 2, so we can put this equation 3, which is this value, from equation 3. What we will get is, finally we will get modulus Vs e raised to power 0 to be nothing but equal to L di by dt modulus of space vector Is j phi and j phi plus L omega e raised to power j phi plus what we have is I think we have left one term j here, and this goes there, that's it. So that will be j here, this will be j here, and this will be again j over here. Now this, when we do on this side, plus we take from the other side r I is e power j phi plus v converter e power j delta. Now we can represent this term. So we look, j phi is nothing but modulus cos phi plus j modulus sin phi. And if we see, what does it indicate? It indicates that, if we see what does it indicate, it indicates that we have this term which is ISD, nothing but modulus of Is, or the magnitude of Is space vector, and cos phi. And if we take the q component of this, so this one will be nothing but Isq modulus Is sin phi magnitude. So this is what we can write over here. This Is, this one is nothing but Isd, and Is sin phi is nothing but j Isq. And we know that this is nothing but a modulus, or the magnitude of voltage space vector angle Ej0 is nothing but angle 0 is nothing but Vsd plus j sin 0 is 0 is j0, I mean Vsd, and where Vsd is nothing but modulus Vs cos of 0. Similarly, we can write down for V converter plus V converter e raised to power j delta to be modulus, or your magnitude of V converter, or magnitude of a space vector V converter, cos delta plus j plus of V converter sin delta, and that is nothing but V converter along D, V converter component along D, and V converter component along Q. So this we can see, this V converter, if we take the V converter component, let us take the red color. So if we take this this V converter, so this is, but V converter D component is nothing but modulus of V converter cos delta, and this if we take on Q component, so this is nothing but V converter over Q component, and that is nothing but magnitude of V converter space vector times sin delta, and that is what we have written over there. V modulus V converter sin delta is nothing but V converter Q component. So now let us take this particular equation, equation number 4, and try to write down in terms of D and Q component. So our left hand side will become Vsd plus j0, and right hand side will become L d by dt ISD plus J ISQ plus R ISD plus J ISQ plus this term is there J L omega ISD plus J ISQ, and our this one is V converter D plus JV converter Q. Then we can just VSD plus J0 L di by dt ISD plus J L di by dt ISQ plus R ISD plus J R ISQ. So here it is RS, here it is RS, no. So we have to take the RS component. So this is RS, this is RS, this is RS, this is RS, this is RS plus RSQ plus V converter D plus JV converter Q, and this term, so J omega L ISD and J square will be minus, so minus omega L ISQ. And since this D and Q axis are 90° apart from each other, so we can separate out this D component and Q component, D axis component and Q axis component to get the D axis model and Q axis model. So then we can write, we can separate out real and imaginary part. When we separate out real and imaginary part, what we will get with just the real part, VSD L d by dt ISD plus RS ISD plus V converter D plus or minus omega L ISQ. Similarly, imaginary part, 0 to be equal to, if we take L d by dt ISQ plus RS ISQ plus V converter Q and omega L ISD. Now what we can do is we can rearrange this term to actually get, so if you rearrange this term, so it is the V converter and Q converter which you are applying. So when we write down these things, what we will get is, you know, L d by dt ISD plus RS ISD, if we take to the other side, minus V converter D plus omega L ISQ and plus VSD, and similarly L d by dt ISQ plus RS ISQ, that is nothing but minus V converter Q minus omega T. Now if we look this one, this is nothing but the D axis model and this is nothing but the Q axis model, these two part, and here we are applying the the voltages across the L and RS, and what we see is that in the D axis model all the terms are D axis except one term which is this one, and that is the cross coupling term. Similarly, in Q axis model all the components are Q component except this term which is the cross coupling term. So then whenever we are making the closed loop control, we must ensure that this cross coupling term need to be properly managed. We will discuss that when we discuss the closed loop control. But what you see is that we have derived the two axis model where we are applying two voltages from the, we are applying the D axis, we converted D axis, and we have the supply voltage VSD along the L and RS along the inductor and resistance, while in the Q axis we are applying the Q component of V converter and the Q component of Vs space vector is 0. So what we see is that we will define the two axis model, and now in this one, if we are changing this ISD, there is no impact we will see on the ISQ, and if we are changing the ISQ, there is no impact on the, because this ISD and ISQ components are 90-degree apart from each other, because these are component of current space vector along the D axis and Q axis. So they are 90-degree apart from each other because D and Q axis are 90-degree apart from each other. And then when you are changing the ISD component, there is no impact you will see in the ISQ component, and whenever you are changing the ISQ component, there is no impact you will see on the ISD component, and that is when we can get two independent circuit models, which is D axis model and Q axis model, and then we can then control this V converter along the D axis and V converter along the Q axis, and thus you can able to control the ISD and ISQ, and this control is independent of each other because D and Q are 90-degree apart from each other. So with this we will get the independent control over the two phases, you can say two different axes, we can get the independent control on two currents, and those two currents, which is ISQ and ISD and V converter D and V converter Q, is actually derived from the three phase quantities, and if we are controlling this two phase quantity, then accordingly my three phase quantities will be changed, and in the main advantage what we will get is in the D and Q axis we have independent circuits, so we can control them independently, and that is when in the three phase system we will reflect that independent control in the three phase by making sure we have the the balanced three phase operation, and because we have derived the Q and D component by assuming that we have balanced three phase operation. So this D and Q axis component, whenever you are controlling independently, it will actually reflect onto the three phase quantities in the equal proportional, and that is when you can do the independent control on this, and we will discuss more inference what we get coming out of this derivation in the next class, because that will clear your understanding about how we can do the independent control and how we can say they are independent of each other. There is small cross coupling term, but these terms can be eliminated in the terms of feed forward terms when you are doing the closed loop control. We will discuss those things in the next class. So here in this particular lecture we have derived two axis model, and D axis model and Q axis model, and those two axis models are quite independent of each other because the quantities which are used here are independent of each other in both the circuit models, and that is when these circuit models are independent of each other. We will discuss this in further detail in the next lecture. Thank you.